The speaker of today is Alex Grilo, and he's going to talk us about recent advances in zero-knowledge protocols in the quantum settings. So thank you, Alex.
So thanks for having me. Unfortunately, this is online. I didn't manage to visit Singapore, but let's try to make it. And I copied the title from a different previous talk, and I put there it was recent. Here is not so recent, so I think I'm presenting things from 2019. So it's rather recent, but not like really fresh. As the title says, I'll talk a bit about quantum zero knowledge, and quantum zero knowledge lies in the intersection of these three big topics like quantum computing and quantum information, theoretical computer science, and cryptography. So it's very multidisciplinary, and for that I'd like to start from scratch, because I think there are a lot of people who don't have either of this background. So, and please ask questions if something is not clear, or even if things are like too basic and I should move fast, also let me know, like I can adjust the pace. And to start from the beginning, let me talk about a bit interactive proofs. So probably all of you know about the complexity class NP, where we say that a language or a problem is in NP if you have a polynomial time verification that receives a proof, a polynomial size proof from a prover. And after receiving this proof, like this verification algorithm decides to accept or reject. And what you want is that for yes instances, or for inputs that are in the language, there exists a message that the prover sends that makes the verifier to accept. And for all instances that are not in the language, no matter what the prover sends, then the verifier rejects. Okay, so this is like a standard definition of NP. But later, cryptographers and computer scientists, they realized that, okay, why do we need just to make this communication from the prover and the verifier? Why can't we generalize it to several rounds of communication? And then people defined a complexity class called IP, where this is exactly the thing that we have is that we have a prover, have a verifier that exchange messages back and forth. So we still have the verifier to be polynomially bounded. We have the communication between the verifier and the prover. It has like the whole transcript has to have a polynomial size, but the prover could be unbounded. So the prover could take exponential, double exponential, whatever time they want. And again, what we want is that for yes instances, there exists a strategy for the prover that makes the verifier always accept. But for inputs that are not in the language, no matter what the prover does, the verifier should reject with high probability. And I just forgot that I didn't mention that here we usually we have to consider verifiers that are randomized, and we have to consider give the verifier some slack, and for no instances, the verifier could make some mistakes, but with very low probability. And what's very surprising is that this complexity class that encompasses all problems that have interactive proof systems is actually equals to P space. So it's pretty big compared to NP. So everything that can be solved with polynomial space has an interactive proof system. Okay, and this is a very nice characterization of this complexity class. So starting from interactive proof systems, a zero knowledge protocol is just like an interactive proof system with an extra property. And the property is that the verifier, like this learning algorithm, is learning nothing when the input is positive. Okay, so the idea is that if after the verifier interacts with the prover, of course, the verifier will learn if it's a yes and no instance. But when it's a yes instance, or when you're like post-selecting to this case, the verifier is learning nothing else. Okay, and this is a very hand-wavy definition, and we'll see what it means to learn nothing, like how to have a proper definition of a verifier learning nothing from interacting with the prover. Okay, and usually, especially in cryptographic settings, we usually want that even malicious verifiers that do not follow the right protocol would not learn anything from the prover either. So what we want here is zero knowledge against even malicious verifiers. Any questions so far? Okay, So let me define zero knowledge more formally. So as I said, we have this interactive proof system with a verifier that decides to accept or reject, but we might consider a malicious verifier that just interacts with the prover. And we consider that the verifier, this malicious verifier, just outputs some string X, or like it outputs from some distribution X. And to say that the protocol is zero knowledge, what we want is that there is a simulator that might depend, or that depends on the verifier. So for example, it could interact with this malicious verifier in a black box way. And this simulator should output some string that comes from distribution Y. And we say that like this, a protocol is zero knowledge if you can construct such a simulator such that the output of the verifier interact with the prover is indistinguishable from the output of your simulator. And this indistinguishability, it can come from different flavors. So for example, we can talk about computational zero knowledge, where we're just saying that for any polynomial time algorithm A that receives either a sample from the interactions with the prover, so a sample from the output of the malicious verifier, or a sample from the output of the simulator, this polynomial time algorithm cannot distinguish which sample it received. So the probability, the advantage of distinguishing these two should be negligible in the size of the input. Okay, so this is what the computational zero knowledge property that would have from such a simulator based on this verifier. Any question? Okay.
So N is the size of the communication between.
No, sorry.
N
is the size of your input. Like you have to you do the zero knowledge protocol for deciding the X is in the language or not. So N is just the size of the input.
Okay.
But okay, here we have computational zero knowledge, but we can be but for cryptographic assumptions, we need a bit more, a bit stronger requirements, and we want this to be true even if the verifier receives somewhat called like some side information. So we can assume that the verifier receives this non-uniform string Z that comes like false from Sky. And we give the same string Z to the simulator, and we want that even when both are given Z for all Zs, the simulator, the output of the simulator should be indistinguishable from the output of the verifier. Okay, but this is just usually this is not so important. But for applications, yes, but for devising zero knowledge properties, this might not be so important.
Excuse me, is this for
yes.
composable security or is that?
Yeah, for example, yeah, if you need sequential composability or put this zero knowledge protocol in other things, this is very important.
Okay, thanks.
Any other question? Okay, so yeah, I mentioned that this is what we call computational zero knowledge, but we can have more strict definitions. And for example, we can ask for statistical zero knowledge, which asks that the two distributions of the outputs, they're actually statistically close. Okay, not only they're not distinguishable by point in time algorithms, actually even unbounded algorithm would not be able to distinguish them. Or we can ask like the most restricted version of zero knowledge called perfect zero knowledge, where the two distributions are exactly the same. And it's surprising that sometimes we do have some, we do have perfect zero knowledge protocols for specific languages. And let me just give zero knowledge is very important in cryptography, and it has several applications. And let me just give a very simple way where zero knowledge can be used. So imagine that Alice, she has some input X, but she doesn't want to reveal X to B. And she wants to send just Y, that's f of X. So B would learn Y, but it would not reveal X. Okay, the idea is that, okay, not more than Y would reveal X. So usually in cryptography, you can just how can B trust that Y is actually a pre-image of F? How can B trust A that Y was computed correctly? So we can use zero knowledge proofs to say that, okay, A, you prove in zero knowledge that there exists some X such that Y is equal of X. And this, if F can be implemented efficiently, this is an NP statement. And for example, one would be able to use this zero knowledge proof. B would be convinced that Y was created correctly, but would not learn X itself. Okay, and because of this, like it's this very versatile type of application, people have proposed zero knowledge protocols, in particular for all problems in NP. And I'll explain now like the classical version, like this classical protocol for zero knowledge for NP, and try to see how people address that in the quantum setting, and then move to the full quantum setting where we're doing zero knowledge protocols for QMA. Okay. So yeah, so I'll move on. So let's have the first attempt. So let's consider like our goal now is to prove a zero knowledge protocol for the 3 coloring problem, which is NP complete. So let's start with the first attempt, where let's just see what happens with the first, like with the vanilla NP protocol for 3 coloring. So imagine the prover just sends the colorant to the verifier. Is this protocol? This protocol is complete and sound because this is the NP protocol for 3 coloring, but it's far from being zero knowledge because the verifier here, intuitively, the verifier is learning the whole coloring, and the simulator would not. If the simulator runs in polynomial time, simulator would never be able to find such a 3 coloring. Okay, so this protocol is very far from being zero knowledge. Okay, because the point is the simulator would have to compute a color in polynomial time, and you assume that P is different of NP. Okay, so this protocol is not good for us. And actually, in order to be able to achieve zero knowledge for NP, we need to use some cryptographic primitives. And the cryptographic primitive that you use is called bit commitment. And bit commitment is some sort of cryptographic safe. So imagine that you have 2 parties, the committer and the receiver, and the committer holds a message M and puts it in a safe and send it to the receiver. Okay, so at this point, the receiver does not know the message M, but the receiver knows that the message M is inside the safe. So the receiver does not reveal it, but the receiver knows that the message is fixed. Later on, when the committer wants to reveal the message to the receiver, sorry, yeah, the receiver has a safe. So later on, the committer wants to reveal the message to the receiver. It can only send the code that opens the safe, and the receiver can finally read the message M. Okay, so the bit commitment allows us to have this 2-phase protocol where first you commit to the message and then you reveal it. And the commitment phase does not like it's hiding in the sense that the receiver does not learn M just in the first phase. And okay, we don't have safes. Okay, we do have safes physically, but like for our cryptographic protocol, we want to have a protocol that implements it. So this is just a protocol between the committer and the receiver. We have 2 phases. We have the commitment phase and the opening phase. And as I said, we want to the hiding is that after the commitment phase, the receiver cannot learn M from the transcript of this commitment. And what we want is also binding, saying that once the receiver has the commit of M, the committer cannot change their mind and open to a different message. So the binding property is that the message M is fixed after the first phase. Any questions? Okay, no questions. I don't know if it's a good or a bad sign, so I will continue, but
it's good, it's good.
Okay. So let's see the zero knowledge proof for 3 coloring. The idea is that the prover is just will first choose a coloring, and one part of it, the very first step is that the prover has the coloring, but it will swap the colors to a random coloring. So it will just map to pick a random color through coloring for that graph. And after it does this permutation of colors, it put all of the colors on safes, like it used bit committance, and send them to the verifier. So it commits to the color of every node. The verifier then asks, picks one of the edges uniformly at random and asks the prover to open the commitments for the nodes corresponding to that edge. So the prover can just send reveal which are the openings for those specific commitments for the nodes of that edge, and the verifier open them and check if the two colors they are different. Okay, and in this case, the verifier accept. Otherwise, if the two colors are the same, the verifier should reject. And you have this protocol is complete, meaning that if the graph is through coloring, there is a strategy of the prover that makes the verifiers always accept, because the honest strategy, the prover always gives a proper through coloring. So every time that the verifier will open one edge, the verifier will see two different colors. The protocol is also sound, and it's sound because imagine that, okay, let's suppose that the graph is not through colorable. So the prover has to commit to some coloring. So when the prover sends this coloring to the verifier, there is one edge that the verifier can choose that would lead to two vertices with the same color, because by definition, every coloring must have such an edge. And the verifier then pick this edge to 1 over the number of edges. So with no negligible probability, the verifier would catch the prover that's cheating. Okay, and now what we'll see is that this protocol is actually computational zero knowledge, and intuitively this happens because the verifier is not learning anything. Like the verifier is just seeing two random different colors, right? Because the prover re-randomized the colors, so whenever the verifier opens, it will just see like two colors that are different and uniformly random. So intuitively, the simulation can be like the simulator. We will see that we can have a simulator that has the exact same view. So far, so good.
So it doesn't matter how small the probability of failure is, right?
Okay, you can. Okay, usually, okay, you can implement it. You can boost it sequentially.
Okay.
Okay, so, and then when you repeat a lot of times sequentially, and then you can make it the error probability exponentially close to 0.
Right. Okay.
But then with more rounds of communication, and yeah, then is a big question in zero knowledge is how to make short protocols. But at least if you don't care about the number of rounds, then with many rounds, you can make it like the soundness goes to 0.
Right.
Okay, so let me, yeah, I don't know how, okay, how I'm going with time, okay. Let me just describe quickly the simulator, like just for you to give a flavor of how to prove zero knowledge. So the simulator that receives this side information Z, it gives it to the verifier. So it's just interacting with the verifier as the prover would. And then the simulator first picks one edge uniformly at random, and it commits to a random coloring that's correct on edge E. So remember that the simulator has to run in polynomial time. It won't be able to create a proper coloring, but when you fix an edge, it's very easy to have a coloring that's correct to that edge, right? You just pick two different colors there, and then you map you color everything else in a different way. Okay. So this is not a proper coloring, but it will commit to this coloring to the verifier. So this is not a good coloring, but it's good at least for that edge that the simulator chose in advance. And then, like when the simulator commits it to the verifier answers back with a challenge, with an edge that they picked uniformly at random. And then if the edge that the verifier picked is the same that the simulator chose, we're good, right? Because you can just open it and the verifier will see two different colors. But if the edges are not the same, we do not have any guarantee. So potentially these two colors will be the same, and this will be problematic because this would lead to rejection, and we want a transcript of a good of a yes instance verification. So if the simulator would open to two colors that are equal, this wouldn't be the same distribution as the verifier would have for yes instances. But what we can do here is just rewind to step 2. So we made a guess and the guess was not correct. So we just go back and try to guess again. So we pick a different edge, not a different edge. You pick an edge uniformly at random again, commit to a coloring to that new coloring that you have that is correct on that edge, and repeat it like this until you have two edges that are the same. So when the guess is correct. And whenever the guess is correct, you just open the commitment and give the output to the verifier. So the only thing that we need to see is that whenever these two edges are the same, the output of the simulator is indistinguishable from the output of the protocol because of the hiding property of the commitment scheme. So the key point here is that since the commitment is hiding, everything that's not open is indistinguishable from us the same color, for example, to the distinguisher point of view. So this random coloring that you committed is not revealing any information about those colors that are not good. And yeah, this is what I said. And since the verifier is computationally bounded, the distribution of E does not depend on the committed value. So it means that the probability of guessing the correct edge that the verifier challenged is roughly 1/m. So it's roughly 1/, the number of edges, right? Because if you pick one uniform at random, and then the verifier will guess it with like the verifier. It will be the same as the verifier challenges with probability 1/m, roughly. And this is a sketch of proof.
Can I ask, did you suppose here that Z is a positive instance or not?
Yeah. No. Yeah, it is a positive instance. Z is the side information, and you have an X that is a positive, like the graph is recoloring.
So then can you just go back? I kind of know the answer, but it may be helpful to the only settle point is 5, yeah? So what's happening if I just stop the protocol at 2?
What do we mean stop at 2?
Oh, so you know, you have to, so what if the protocol is just that I give a random coloring without, you know, rewinding if the edge is not the same as edge prime?
The point is the probability that they're not the same. This is pretty high. Like, okay, it's non-negligible, right?
1 - 1/n square, yes.
Sorry.
Yeah, the probability is 1 - 1/n squared there. And squared
yeah, exactly.
And
so then the transcript would have a very it would be very, like, there is a very easy distinguisher that a very simple distinguisher that would distinguish the simulator that stops like that does not rewind from the real transcript, because with high probability you see two colors that are the same. With non-negligible probability you see two colors that are the same, but in the honest protocol you never see two colors that are the same.
Why do I see two colors which are the same?
Okay, because if you didn't pick the right one, okay, and then you pick a random coloring, the challenge of the verifier will have the same color, let's say with 31/4. Okay, let's say that to send a random coloring. Okay, forget about putting a correct E. Okay, let's say that you're just sending a random coloring. Each edge will have the same, like it will have the same color. Sorry, it's 31/9, right?
Each edge.
No, sorry, 1/3. Maybe I can try to draw. I don't know. Yeah.
No, I mean, it's fine with me if you go on. I just think that, you know, this is exactly the things we will get into trouble in quantum. So that's why I think it's good to make it clear classically, but you know, you can go on from my part. It's no problem.
No, okay. Does anyone else has the same question? I can explain that.
Alex, just go on.
Okay, I'll go on. Okay. So the question is, okay, what happens if the verifier is now quantum? Like, what happens if, like, this simulator is just proving that, okay, this protocol is Zeroknowledge against classical verifiers, but what happens if the verifier is quantum? And for that, we have to first define what means a classical Zeroknowledge protocol against a quantum adversary. So we have a verifier now that's quantum and interacts with this prover. And at the end of the interaction, it outputs some quantum state rho. And now what we want is to have, okay, a quantum simulator. So yeah, to simulate this quantum verifier, we need this quantum simulator that, again, interacts with this malicious verifier and output some quantum state sigma. And again, you could have some side information that here is denoted by the state psi. And the same type of property is required here to have quantum Zeroknowledge. What you want is that for every quantum polynomial time algorithm, A is not able to distinguish rho from sigma. So for every polynomial time A, the probability that it outputs one on A outputs one on rho is this roughly the same as the A output one on sigma. So these two probabilities should be negligible. Like the difference of these two probabilities should be negligible. So, and we can also extend it to the statistical setting, saying that, okay, the trace distance of rho and sigma should be negligible, or a perfect Zeroknowledge saying that these two decimatrix actually should be exactly the same. So this just straightforward lifting of the classical Zeroknowledge property to the quantum one. And let's see what happens with the simulator when you have to prove Zeroknowledge for it. So let's just take the same simulator and assume that V is quantum. So it turns out that, okay, okay, V is just running like is a quantum algorithm that runs this. Sorry, S is a simulator is just a quantum algorithm that is running this circuit, and the state just before sending the challenge is just before the verifier changes the challenge is E prime, where E prime is the message sent by the verifier, and some state gamma E prime that's chosen from the verifier. Okay. And here, this step 5 is doing a test if E is equal to E prime, right? So the simulator would have to measure this bit to decide if E is equal or not to E prime. And again, if E is equal to E prime, everything is good, because okay, then we are in the case where the simulator committed to the right graph. But if E is different of E prime, we can not just rewind simply to step 2, because this measurement here, so this measure that if E is equal or different of E prime, disturbs this quantum state. So we have that applying V dagger to E prime gamma prime E, sorry, gamma E prime, there's a typo here, is different of rewinding the whole state, the whole superposition that the verifier had. Okay, and this disturbance of the states forbids us to simply rewind, like in a straightforward way, to rewind to step 2. Okay, or even resetting angle to step 2. This is just not possible because the state has been disturbed. So this simple simulator does not work with quantum or with quantum side information, and okay. In the quantum setting, quantum side information is crucial if you want sequential repetition and if you want to boost the probability, for example, with the question like the question that João had. Okay, so we need some smarter idea in order to reach quantum zero knowledge. And this was it was exactly what Watchers did in 2006. So the Watchers proposed this quantum rewinding technique, where let's assume that you have a quantum circuit that it has some that there exists some P. So you fix the circuit Q. What it shows that if there exists a P such that for every input state psi, Q on psi 0 is of the form square root of 2P phi 1 phi 0 that depends on psi, like this quantum state depends on psi, plus 1 minus square root of P1 phi 1 of and another state that depends on psi. So the key point is that when you apply Q on psi 0, you have the first bit to be 0 with the amplitude square root of P, and the probability of the second bit to be 1 is 1 minus square root of 1 minus P. Okay, so this is the assumption of the quantum rewinding. And what Watchers showed is that if this is true for every psi, then we can construct a circuit R that's not much bigger than Q, such that on input psi, it selects the state like the state phi 0. So instead of like, if you would just simply measure the first qubit, you have phi 0 with probability P and phi 1 with probability 1 minus P. But what Watcher said is that there is a way of steering towards phi 0 with very high probability. Okay, with some probability that depends logarithmic on the, like the size of R depends logarithmic on this error probability. Okay, and this this was the key result proved by Watchers that allowed us to do and this something like this also works in a non-exact case, but this this idea already allowed him to prove with the quantum zero knowledge of three-coloring protocol. And let's see how he did so. So we have this first simulator that is exactly like it was very similar to what Miklos said. So it performs correctly until the point you have to check if the guess was correct. So if the challenge is equal to the guessed edge, and if in this case the simulator performs efficiently, like performs honestly. But if it does not, the simulator just aborts. So it outputs, let's say, some perp. And it turns out that the guess was correct. In this case, the guess must be correct with probability. If the guess is correct, then the simulator is fine because the simulator is doing exactly what they want a supervisor would do. And it turns out that the simulator succeeds with probability that's roughly 1/m. Okay, so we have a simulator that's not good enough because the success is not so big, but when it succeeds, then we're good to go. Okay, so going back to Watchers rewinding, this is exactly the setting. So we have this this case where we want these two edges to be equal. So the 0 case is like E is equal to E prime, and P in this case is 1/m. Right, so the probability of having these two that are the same. And exactly what we're looking for is the state where you post-select the measurement on 0. Okay, so just using like a second simulator that applies Watchers rewinding on sim1, we have that the output of sim2 is negligibly close to post-selecting when E is equal to E prime. So the output, in other words, the output of sim2 is exactly what we're looking for. And the runtime of sim2 does not blow up too much. It's just a polynomial in this the size of the circuit v tilde and the input of the state. Okay, so the key point is that of using Watchers rewinding is that you can pick this simulator 1 and boost its probability by using some sort of phase, like some sort of, the techniques come from Gover. So using this type of techniques, Watchers rewinding is able to increase the success probability and achieve a simulator that is doing exactly or almost exactly what we were doing in the honest run. So yeah, I think I should pause for questions. No questions? Yeah, I don't know if, yeah. Okay, I'll continue, but yeah, I would be very happy to have a question now. Okay. So just to sum up, like what you showed in 2006 is that assuming post-quantum commitment schemes, like bit commitment schemes, then you have this 3-column protocol that's secure against quantum adversaries. And my main goal now is showing that you can have a zero-knowledge protocol actually for quantum proofs. Okay, so quantize the results, not for NP, but for QMA. So yeah, let me define QMA. So this is just the quantized version of NP. What you want is that you have now a quantum verification algorithm that receives a quantum proof from the prover, and using this quantum algorithm, it decides to accept or reject. And what you want is that for yes instances, there exists some quantum proof that makes the verifier to accept. And for no instances, no matter what quantum proof the prover sends, the verifier should reject with high probability. Sorry, yeah, in the first case, it's also with high probability. And okay, QMA is a straightforward lifting of NP to the quantum setting, but it also is very meaningful. Like it has very relevant, physically relevant complete problems. So it's an important complexity class. And again, in the quantum setting, people studied what happens if instead of just sending one quantum message to the verifier, the prover and the verifier send 10 messages back and forth, and with the same type of completeness and soundness. So for yes instances, there is a structure of the prover that makes the verifier accept with high probability. And for no instances, no matter what the prover, what's the strategy of the prover, the verifier should reject with high probability. And perhaps surprisingly, it happens that actually QIP, like the quantum version of IP, is actually equal its classical version. So both are equal to P space.
For the QIP setting, so the verifier accepts with high probability or accepts with certain?
I think here it can be 1. Like okay, without loss of generality, you can assume it is probability 1.
Okay.
And okay, and it yeah, one can turn every QIP protocol in a different QIP protocol that has acceptance 1 probability. For the yes case. For the yes case.
Okay. Can it do the same for QMA?
No, we don't know how to do it. So
why not?
Okay, we don't know. Yeah. No, okay, we don't know if it's true or not. No, so there is a complexity class called QMA1, and it's an open question if QMA1 is equal QMA. The point is, here the interaction is allowed. So the prover can give some information that allow you to boost from almost 0 to 1. So we can do some sort of like Grover, some sort of that allow you to boost here, but you need interaction for that. You cannot just from one message from the prover to the verifier, you cannot do that right away. Yeah.
Right. Okay. It comes from interaction.
Yeah.
Okay. Thanks.
Other questions? So again, we have okay. We want now to study zero knowledge, but about these quantum protocols. So it's very similar to what I mentioned before. Like you have this output, this quantum states as outputs of the verifier and the simulator, and you want it to be indistinguishable. The only difference now is that the prover is also quantum, but for zero knowledge does not really matter too much. So zero knowledge just care, like zero knowledge property just cares about the dishonest verifier. So we're good enough with the old definition. So this does not change. And as I said, our goal is to have now quantum zero-knowledge protocols for QMA. So it has a very successful, like zero-knowledge has very success classically. So let's try to do, see what we can do quantum. And okay, then you have to think, okay, if you think about classically, you had this three-coloring protocol. So let's try to do a quantum zero-knowledge protocol for a QMA complete problem. Oh, sorry. First, okay, let's ask ourselves if one could do zero-knowledge from a generic QMA problem. And this is not good enough because we need structure to prove zero-knowledge protocols. For example, classically, we had for three-coloring. So we can pick the most important QMA complete problem, the local Hamiltonian problem, and we can ask ourselves, can you do zero-knowledge for it? And this is not, okay, we don't know how to do so because we need a bit more structure. The local Hamiltonian problem does not give us too much structure to have zero-knowledge protocols. Notice that, okay, when we say that we have zero-knowledge protocols for NP, for all class of an NP, is because all problems in NP, they are reduced to three-coloring. And we have a protocol for three-coloring, but it's not that you know how to do zero-knowledge protocols for like any problem in NP, like natively somehow. So we need structure. And what people did in the past using like zero-knowledge, doing zero-knowledge protocols for what a variation of this local Hamiltonian problem called Clifford local Hamiltonian, which works, but it's somewhat complicated. So it's not a very simple, like this, the three-coloring protocol is rather simple. So we would just put things on safe and send open the safe and so on. And this protocol is much more complicated. And the option that we'll be choosing is doing zero-knowledge for a protocol, for a problem called consistence of local density matrices, which is, yeah, I'll define it in the next slide. But as you see, it will be suitable. Like it's the straightforward choice to have protocols for quantum zero-knowledge. The big question was showing that this problem is QMA hard, and this is actually the heart of our like the main technical contribution for our paper, showing that this problem of consistence of local density matrices is QMA hard under CARP reductions. So let me define this problem. So the input to the problem is the description of local density matrices on k qubits. Okay, so you have the description of several pieces of a potential quantum state. Okay, so k is a constant. So you have just a description of the reduced density matrix on qubits 1, 10, and 12. Another one, the 12, 50, and 55, and so on. So you have a bunch of descriptions of local density matrices. And you want to output yes, so you want to like the yes instances are these reduced density matrices that have a global quantum state. So these are the density matrices for which there exists some psi, such that when you trace out all the qubits that are not corresponding to that rho I, these two density matrices, they're close. So they're like, even like we could ask that they're exactly the same. And the no instances, so the case that we want to reject is that the inputs of like the set of reduced density matrices for which every quantum state, for every quantum state, there is one local density matrices that does not match. So there exists one of these local density matrices such that the trace of this global state on the corresponding qubits is far enough from your input. Okay, so is the definition of this problem clear?
Yes.
Okay, so Liu showed in 2006 that this problem is in QMA, and he showed that this is QMA hard under Turing reductions. But for zero-knowledge, Turing reductions are not good enough. To show that you have zero-knowledge protocols for all problems in QMA, you need CARP reductions. And that's exactly what we showed like in this paper from 3 years ago, is that this problem is actually QMA hard under CARP reductions. Okay, so yeah, I think I have 10 minutes. So let me try to go like to the I'll first try to explain the zero-knowledge protocol for this problem, and I probably won't have time to prove QMA hardness. but yeah, I might sketch it anyway. Let's see.
A quick question from the problem statement. I mean, it's not clear if the number of reduced densities play a major role or not.
Sorry?
I mean, you can have, I guess you can have very few, many reduced density, right?
So
like,
yeah, M, okay, sure, this is the input. So M, okay. If you have a few, the problem is easy, but okay, the problem starts being hard when you have intersections. Right? This is the hard, because if all these matrices they are tensor product, then it's obviously a yes instance.
Right. Yeah.
Right.
Sure.
So if you have a lot of them, then they start intersecting, and then the problems become hard, and then this is the type of instances that become KMA hard.
I see. Okay.
Okay. So let me, any other question? So let me continue. So let me describe quickly how can you put consistent local density matrices in QMA. So the idea is that the prover should send copies. So we have a yes instance, so we have the state psi that's consistent with all of them. So the prover is just supposed to send L copies of psi. The verifier will pick one of these local density matrices uniformly at random, and we'll do some local checks on this qubits corresponding to rho I to check if this part of psi is close to, so is close to, like this part, sorry, this part of psi is close to the corresponding local density matrix. Okay, you can, it's not, we're not doing exactly tomography, but you can think about tomography here. So imagine that you can do tomography and learn the local density matrix of psi, and then you can just compare it with the description that you had from rho I. Okay, and if it is a yes instance, this tomography will always work. Okay, so the verifier should accept with a very high probability in this case. But for soundness, we have that the prover might send, so the prover is supposed to send this tensor product of psi, but a malicious prover, like he's trying to cheat as much as they can, so they can send a very big state sigma that is entangled. But again, what the verifier do is choose some I uniform at random and performs the local check on this big state sigma, but to the corresponding, like the places where it should be, like where rho I should be on each copy of psi. And what one can check is that, okay, this sort of tomography won't pass in this case for the specific rho I that's different, because we know, okay, again, we know that there is one rho I that is for every quantum state. There is a rho I that is incompatible or with that quantum state, and what we can show is that for every quantum state sigma that you do, this tomography will fail with high probability or with some probability. So in particular, what we show is that the verifier accepts this probability that's is roughly 1 minus 1 over m. Okay, so and this 1 over m comes from like this specific, this unique, like this density matrix that's incompatible with like a specific quantum state that construct from sigma. Okay, the key point, okay, the punchline that I need for our next slide is just showing that, okay, for the QMA verification for CLDM only needs to check the reduced density matrices of a specific rho I. Okay, this is the key point that you need from of CLDM to prove zero knowledge. Okay, so questions? Okay, yeah, I think I have seen João, he left. I don't know if okay, can just someone give a sign of life or something? Okay,
yeah, you can,
okay, no, I
you
can
can
see
go on.
Good, yeah. So yeah, let me show how to simply lift like this zero knowledge protocol for through coloring to this CLDM. So we have the prover. We have these copies of psi that is a state that is consistent with all of these local matrices rho 1 up to rho m. And the prover will do some sort of like, when you're doing commitment, you cannot really put these qubits on safe. So what you have to do is you have to one-time pad them. So you apply random Paulis on it. But then you keep all these Paulis and you put, you put all the key of the quantum one-time pad and put them on safe. So you do the bit commitment of the Pauli key to that one-time pad's psi. And the point is, whenever you put like these, when you put the keys to the one-time pad key in the safes, then your new quantum state is a totally mixed state. So in particular, this totally mixed state reveals zero information outside. Okay, and the prover just sends this whole this one-time padded state with the safe, with the committed keys to the one-time pad, and of course keeps the keys to himself. The verifier then picks one of these one row y from these matrices, and then he has the prover open all the positions that correspond to the one-time pad keys of the qubits corresponding to row y. Okay, so the prover then opens all the one-time pad keys that are corresponding to row y, and once the verifier has these values, the verifier can just undo the quantum one-time pad and just do the QMA verification for that specific row y. Okay, and the key point is that for the QMA verification, all the other qubits that are not open, like that, all the qubits for which we don't have for which you don't have the true density matrix, they are not really used in the QMA verification. So that's fine. Like we can proceed without them. Okay. So the zero knowledge proof is the same thing as almost the same thing as the classical one. It's just that the simulator, you have one simulator where you just guess which is the choice of density matrix that the prover will choose, or the verifier will choose. Then you do the commitment of a state that has row y in the right position. So you have the classical description of row y, so you can just and row y has only constantly many qubits, so we can just create a quantum state that is that is correct on that marginal. And whenever you receive a challenge, you're fine if the challenge is equal to your guess, and then you can just proceed with the normal protocol, or you abort. And the guess, like the probability that you guess correctly, is 1/m, and then you can just boost this probability with watches rewinding. Okay, so the idea here is that once you have the complete problem that has the same some sort of the same properties of through coloring, but in the quantum setting, then the same simulators would do the job. Okay, so the key point was proving QMA hardness of CLDM. Yeah, I don't think. How much time do I have? 5 minutes?
Yeah, I would say 10, since we started
okay.
5 minutes late.
Okay, so yeah, I can. So the point is, I can go through the QMA hardness of CLDM, but this will become more technical than, like, it was already a bit technical, but it will become much more. So if people are fine, I can do it, or if you're tired, I don't know. I'm happy with both ways.
Well, what is the alternative?
No, the alternative, I'll go to conclusions or something like that. Yeah.
No. Okay. So
okay. Let me do it. Okay. So one of the, I'll explain now how we prove the hardness of CLDM. And the key object that we need to create to prove this hardness is what we call simulatable codes. And let me describe what's the property of a quantum error correcting code to be simulatable by this example of STIN codes. So STIN code is just the mapping 0 to this big quantum state and 1 to the other big quantum state. Okay, the exact quantum state is not important. But what's like the property that one can check for STIN code is that if you pick any 2-qubit state, any 2 qubits of an encoding of some state psi, the state corresponding to these 2 qubits, no matter which qubit you choose, is the identity. So it's a totally mixed state. Okay, so the reduced matrix of the encoding of state psi is fixed no matter which psi you choose. Okay. In particular, since we know its identity, we have that the reduced matrix of 2 qubits of any encoding of a correct code word of psi can be efficiently computed, right? One can efficiently simulate having identity, right? You have a very, you can even compute the matrix of the reduced matrix of these 2 qubits. Okay, so this is a not so hard, I don't know, observation, but the idea is that we're going to generalize it now. Okay, because the problem is that whenever you have 3 qubits, then it starts being a problem. When you have 3 qubits, now you cannot simulate it anymore. Because if you pick, for example, the first 3 qubits of the encoding of 0, you have the 0, 0, 0 here, but you don't have the 0, 0 below. So these 2 density matrices, they are different. So the goal of simulatable codes is defining error correcting codes for which you have this property that you can simulate all density matrices up to K. So we say that for fixed S, we have that error correcting code CS that is S simulatable. If you can simulate all, So our question is having a fixed S, having error correcting codes that you can simulate every S qubit reduced matrices of all correct code words. And the idea, the way that we managed to, that one can construct this as simulatable codes is just doing concatenation of, for example, STIN code. So, for example, when you concatenate it twice, so every qubit of the encoding of psi is encoded again using STIN code. And whenever you look at 3 qubits of these of the encoding of the concatenated STIN code of some state psi, we know that it comes from the encoding of the totally mixed state of the first qubit. So one can show that for any here that any 3 qubit reduced density matrix can also be simulated. So you have an algorithm that outputs the classical description of the total of the reduced density matrix of any reduced matrix that of at most 3 qubits on the concatenated encoding of psi. Okay, and what we showed in this result with Slofstra and Yuen is that for large enough K, it's possible to compute the reduced matrix of any coder of the K-fold concatenation code of any set of S of at most S qubits, where S where S is linear in K. So S is order of K. Okay, so just to summarize, what we show is that we can construct error correcting codes for which you can output the classical description of all code words on at most S qubits, and in particular, the reduced matrices, they are independent of the encoded state. And what we need in order to achieve like our result, we not only need to simulate the error correcting codes, we also need to simulate like computation on encoded data. And one nice property of the STEAM code, for example, or concatenated STEAM code, is that it allows transversal Cliffords. So for example, if I have the encoding of some state psi, and I apply Hadamards on each qubit of this encoding, then I have actually the encoding of the Hadamard on state psi. So here we say that you apply Hadamard transversally on this code. And what we need from the simulatable code is not only you're able to simulate the reducers matrix of code words, but you also need to simulate the reducers matrix of every step of the computation, for example, on the transversal application of Hadamards on them or any other Clifford. And in this result with William and Harry, we also show that this is not so hard if you have the previous step. And the hard part, usually with computing on encoded data, is having non-transversal gates. And for that, what we usually do is computing with magic state. So the idea is that if I give you, for example, a T magic state, and I have a qubit psi, you can use this circuit that allow you to compute the state where you apply T, the T gate on psi. So this non-Clifford gate T on the qubit psi. But and this is very useful because if you do it in code, in the encoded version, since every operation here is Clifford with classical control, then you can actually apply the T gate on this encoded state psi that you had. So this T gadget, it does not really care if the state is encoded or not if you apply it transversally. The hard part, in order to show that such a gadget can be simulated, because we have this measurement here, and the measurement in principle would not be easy to simulate, but we have it for the specific T gadget. We have that the output of this measurement is the total emic state, and this it's very technical, but it allows to show that this property allows to show that one can simulate also every step of the computation of this T gadget on the encoded state. So just to summarize, you have this error correcting code where you can simulate the code words, and where you can simulate each step of the computation of applying some gate on the encoded data. Okay, so this is the tools that you need. So let me now show that CLDM is indeed QMA hard. And to show that, we start with a generic QMA problem. So we have a generic QMA problem, just have a quantum circuit V. That is the verification circuit. And we know that circuit V, it receives some initial state psi, and psi is composed by both the quantum proof and the 0 and Scylla qubits. Okay, and okay. One thing that you need from this QMA verification is that we can reduce it to the 5 local Hamiltonian, so we can map this quantum circuit to a Hamiltonian such that the ground state is the history state. So the ground state of the Hamiltonian is the superposition over all snapshots of the computation of V on the initial state psi init. Okay, and we have that the high this Hamiltonian HV, it has low energy if and only if the verification accepts high probability. Okay, and this is not okay. This is not good enough for zero knowledge because it's not simulatable. But as we show next, we can tweak this verification algorithm such that the same sort of construction will give us simulatability, and simulatability will give us the local density matrices. And so here's the tweak that we need to do. So the key point is that instead of running the original circuit from the for the QMA verification, we do now a circuit V prime that will compute on the encoded data. So the idea is that the prover will not send the original witness, but to encode it using a simulatable code. For technical reasons, we also needed to receive, like we need this witness to be one-time padded, but the prover will also send the one-time pad of this key. So the one-time pad keys of this encrypted state. So this is fine, but morally, what's happening is that the prover is sending the encoded version of psi. This new verification is just check first that this encoded witness is correct. To just undo the one-time pad, this is doable because the one-time pad keys are correct, like they are given. And finally, it will just create the encoded version of 0 and T magic states that you need to perform the computation. And once you have all this, like you have the encoded witness and the encoded ancillary states, then you can just perform the local operations that V would do, but now on the encoded data, right? You transversally, you apply Clifford gates, and non-transversally using T gadgets, you can compute T gates, for example. And at the end of your circuit, you would have the encoded version of the output, and you can just decode it, and V prime will just decode the output, and output decide to accept if the decoded output is 1 or reject if the decoded output is 0. Okay, and what we show is that then if this aircraft encode is simulatable, then you can compute the reducency matrices of the history state of this computation. Okay, if and only if this verification accepts the probability for psi. Okay, so let me just roughly say how we do the proof. So we first show that we can simulate every snapshot of your computation. So when you have V prime, then for every step of the computation, you can simulate what's the snapshot of the computation, and then you can leave that to intervals of the history state and finally the history state. So the key point is that we lift from the simulatable codes to simulation of snapshots of our QMA verification, and then we lift from this simulation of snapshots of the QMA computation to the simulation of the history state, and this gives us the QMA hard instance for the CLDM. Okay, so yeah, this is I think it gets a bit more technical, so sorry about that. But this is the QMA hardness proof for CLDM. So just to finish, I'd like just to say that, okay, there's a lot of things that have been happening in quantum zero-knowledge in the I don't know, past 4 or 5 years. But there are plenty of open questions. So for example, we're doing all these zero-knowledge protocols, but it's not so clear that quantum zero-knowledge is just used for as classical one. So we don't have many places where zero-knowledge protocols were a useful tool in cryptographic protocols. So I think there should be, and I think we should try to understand a bit better why we're studying quantum zero-knowledge. There are other technical questions. For example, like can you have what we call a NISIC, like a non-interactive zero-knowledge proof for QMA? When you have standard scenarios, so yeah, I won't get into details because we do have NISICs, but non-standard scenarios. So it's still an open question if you can have it like with a random oracle or a CRS. I think a very interesting and I don't know, fundamental question is understanding if zero-knowledge also holds for non-signaling provers. So in my paper with Slofstra and Yuen, we proved that it works for quantum provers, but for non-signaling is an open question. And finally, okay, can you do protocols that are more practical, that you can, for example, implement in the
Sorry, what does it mean, non-signaling?
Oh, so the provers, the output of the provers, they respect no signaling probability, sorry, no signaling distributions. So a distribution is no signaling if the distribution. So you have Alice and Bob. You give one input to Alice, one input to Bob. Alice outputs A, Bob outputs B. The distribution of A cannot depend on the input of B, of Bob. Okay, so they can have correlations, and correlations that are even stronger than quantum correlations, but they cannot. The distribution of the output of Alice cannot depend on the input of Bob. This is the key point. Okay, and so people have been studying like a proof system with no signal improvers, but the zero knowledge is not clear. Like, yeah, it's not clear if zero knowledge would because, for example, for classical provers and for quantum provers, you can ask for zero knowledge without losing the computational power. But for non-signal, this problem is open. Okay, yeah, and I think with that, I'd like to thank you for your attention. I'm very happy to discuss more and answer more questions.
Well, thank you so much.
But in your proof, you use STIN code, right?
Mm-hmm.
Could you use other codes?
Yeah, you can use other codes. Okay, actually define simulatable codes, and then we show that for any simulatable code, the proof works. And then we just show that concatenated STIN code is a simulatable code.
Right.
You just need a code where you can do transfer. Like, yeah, we need to be able to compute on that code, and then I think this should be good enough.
Do you think that by using other codes, you can extract more out of the proof?
Okay, there are a few technical questions for the CLDM hardness that we haven't solved. Is that, for example, when you do the reduction, the quantum state for yes, is the quantum state that's consistent with the local density matrices. It is actually a mixed state. Okay, so one thing, and this comes somehow from checking the encoding and this one-time pad, like these technical things, as I said, that they somehow makes that the global state is mixed. I think that one thing that could be better is that, like, maybe with good codes or even with STIN codes, but proving extra properties, is that the global state is a pure state. It won't change too much for complexity theory or for cryptography, but I think that it will be fundamentally interesting to understand if you can do that or not.
Okay. Interesting. Would it give something extra, or just out of curiosity?
No, of course, then it could be more efficient and so on. So we can do that, like, but not asymptotically and not I don't.
Right.
Because at the end of the day, we prove the result using simulatable codes. That's this general thing. So not clear if some, like, proving that other codes are simulatable, I don't think it, I'm not sure that it would help.
Okay. Thanks.
So I guess let's thank Alex again. Yeah. Hope to see you here at some point.
Okay, yeah. Thanks for inviting. I hope the talk was not zero knowledge, but okay.
Thanks a lot.
Thanks, Alex. Thanks for the talk.